Welcome friends. In this unit, we discuss formal definition of continuity. One of the most important class of functions in real analysis is the class of continuous functions. Work of Bernard Bolzano in 1817 and Augustin Louis Cauchy in 1821 identified continuity as a very significant property of functions. In everyday speech, a continuous process is one that proceeds without gaps of interruption or sudden changes. The idea of continuity in the context of function means that we can draw the picture without lifting the drawing instrument like pen or pencil. Suppose we have a real valued function f defined on some interval. Such a function can be represented by a graph in the Cartesian plane. Figure A1 and B1 are drawn smoothly without pen lift. But in figures A2, A3 and B2, B3, there are breaks or jumps at points x equal to A and x equal to B. Let us try to explain this mathematically. The breaks or jumps show that small changes in the input values of x can produce broken jumps in the changes of output values f of x. In figure A3, consider neighboring points of f of a. These points can be obtained by drawing epsilon band between the horizontal lines y equal to f of a minus epsilon and y equal to f of a plus epsilon for a convenient small positive real number epsilon. Now consider a delta band between the vertical lines x equal to a minus delta and x equal to a plus delta for a positive number delta. There exist values of x in this delta band for which the output values f of x are not in the epsilon band. This is true for any small positive number delta. This should not happen in the case of a continuous function. So a continuous function is a function in which arbitrarily small changes in the input produce arbitrarily small changes in the output. In figure A1, we can see that for any epsilon band containing f of a, there exists a delta band such that x belongs to open interval a minus delta to a plus delta implies that f of x belongs to open interval f of a minus epsilon to f of a plus epsilon. That is, absolute value of x minus a less than delta implies that absolute value of f of x minus f of a less than epsilon. A form of this epsilon delta definition of continuity was first given by Bolzano in 1870. Preliminary forms of related definitions of the limit were given by Cauchy. It was the careful work of Carl Weierstrass in the 1870s that brought proper understanding to the idea of continuity. Now look at the formal definition. Let A subset of R the set of reals. Let f from A to R be a function and A belongs to set A. Then f is said to be continuous at A belongs to capital A if for each epsilon greater than 0 there exists delta greater than 0 such that absolute value of f of x minus f of a less than epsilon whenever for all x belonging to capital A for which absolute value of x minus a less than delta. The function f is said to be continuous on A if it is continuous at every a belonging to capital A. If f fails to be continuous at A, then f is said to be discontinuous at point A. We can make the notes. 1. The values of delta depends upon the values of epsilon and A. Second one, the function must be defined at x equal to A. Remark, if f is not continuous at A, then there exists one epsilon greater than 0 and a point x in the set A such that for all delta greater than 0, 0 less than absolute value of x minus a less than delta implies that absolute value of f of x minus f of a greater than or equal to epsilon. Let us consider an example that examines the continuity of the function f of x equal to 5x minus 3 at x equal to 1 in the closed interval 0 to 2. F of 1 equal to 2. Let epsilon greater than 0 be given. If we can find delta greater than 0 such that absolute value of x minus 1 less than delta implies that absolute value of f of x minus f of 1 less than epsilon, then the function is continuous. Now, absolute value of f of x minus f of 1 is equal to absolute value of 5x minus 3 minus 2 equal to absolute value of 5x minus 5, which is equal to 5 into absolute value of x minus 1. We can refer this as step number 1. From 1, it follows that 5 into absolute value of x minus 1 is less than epsilon, implies that absolute value of f of x minus f of 1 less than epsilon. That is, absolute value of x minus 1 less than epsilon by 5 implies that absolute value of f of x minus f of 1 less than epsilon. Therefore, if we choose delta equal to epsilon by 5, then absolute value of x minus 1 less than delta implies that absolute value of f of x minus f of 1 less than epsilon. So, the function is continuous at the point x equal to 1. Let us check the continuity of the function f of x equal to x square if x not equal to f of x equal to 1 if x equal to 2 at the point x equal to 2. Here f of 2 equal to 1, let epsilon greater than 0 be given. We have to prove that there exists delta greater than 0 such that absolute value of f of x minus f of 2 less than epsilon whenever absolute value of x minus 2 less than delta. Now, absolute value of f of x minus f of 2 equal to absolute value of x square minus 1. But absolute value of x square minus 1 less than epsilon implies that 1 minus epsilon less than x square less than 1 plus epsilon. This implies that root of 1 minus epsilon less than absolute value of x less than root of 1 plus epsilon. This shows that either root 1 minus epsilon less than minus x less than root 1 plus epsilon or root 1 minus epsilon less than x less than root 1 plus epsilon. That implies either minus root of 1 plus epsilon less than x less than minus root of 1 minus epsilon or root 1 minus epsilon less than x less than root 1 plus epsilon. If we choose epsilon less than 1, then 1 plus epsilon less than 2, and so root 1 plus epsilon less than 2. So, the point x equal to 2 is neither included in the interval minus root of 1 plus epsilon to minus root of 1 minus epsilon, nor in the interval root of 1 minus epsilon to root of 1 plus epsilon. So, there does not exist a delta greater than 0 such that absolute value of x minus 2 less than delta implies that absolute value of f of x minus f of 2 less than epsilon. So, the function is not continuous at the point x equal to 2. We can make the following remark. The notion of continuity of a function defined on interval can be analyzed by looking at the graph of the function at each of its points. The properties of these graphs are: 1. F of x is defined for x equal to a. F of x is defined for all values of x near x equal to a. If x approaches the value a from either side, then f of x approaches the value f of a. These are observed from the picture. So, the concept of continuity of a function defined on an interval can be defined in terms of limit of a function. Definition: a real valued function defined on an interval I equal to closed interval a to b is said to be continuous at a point c belonging to open interval a b if limit x tends to c f of x equal to f of c. We can make the following remark. From the above definition, it follows that a function f from closed interval a b to r is continuous at a point c belonging to open interval a b if left limit, right limit exist and they are equal to f of c. That is, limit x tends to c minus f of x equal to limit x tends to c plus f of x equal to f of c. Now, we can define the continuity at the endpoints. A function f from closed interval a b to r is said to be continuous at a if limit x tends to a plus f of x equal to f of a. A function f from closed interval a b to r is said to be continuous at b if limit x tends to b minus f of x equal to f of b.